Let us see how NMR spectroscopy works. Suppose let us take this is the y-axis and this is the z-axis, and we are going to apply the external magnetic field along the z-axis. When we apply the external magnetic field, now the nuclei can have one of the orientation such that its rotation is parallel to the applied magnetic field. So this state being parallel to the external magnetic field will have the less energy and more stable. But at the same time, the nuclei can also have an another orientation where the nuclei will have an opposite rotation so that it is having the higher energy and less stable. Now this orientation where the rotation of the nuclei is aligned with the orientation of the external magnetic field is called as the ground state or alpha orientation, and I is given as plus half. And another orientation which is having the opposite orientation to the applied magnetic field will have the beta orientation, and it is given I value as minus half. So under the applied magnetic field, a nuclei can have either plus half orientation or minus half orientation. Now let us see how NMR spectroscopy works. In order to understand the NMR spectroscopy, we have to define few of the other parameters. So first one, spin quantum number I. So we have seen that I should be half in order to show the NMR signal. Second is the spin angular momentum S. Each spin state will have some angular momentum. So S is given by h by 2 pi into I. And third one is the magnetic moment number M. Already we have defined this. M is equal to 2I plus 1. Magnetic momentum mu. Each spin state will have some magnetic moment, and the magnetic momentum mu is given by gamma into S, where gamma is the gyromagnetic ratio and S is the spin angular momentum. And finally, each spin state of a nuclei will have some energy, which is nothing but the magnetic energy E is given by mu into B naught, where B naught is the magnetic field strength we have applied externally. So by using these parameters, now we can easily understand how this NMR spectroscopy works. Now we know that for a nuclei to show the NMR signal, I should be equal to half. So when I is equal to half, the number of spin states M is equal to 2 into I plus 1, which is nothing but 2 into half plus 1, so which gives 2. So when I is equal to half, the nuclei will have the 2 spin states. So one of the spin state will have a spin quantum number as plus I, and another spin state will have a spin quantum number as minus I. Now the nuclei will have the 2 spin states, I is equal to plus half and I is equal to minus half. For each spin state, we can write the spin angular momentum as well as magnetic momentum. So spin angular momentum S plus half is equal to h by 2 pi into I. So here the I value is given as plus half, so we can substitute the plus half. So then it becomes plus h by 4 pi. Similarly, S minus half is equal to h by 2 pi into minus half, so which is equal to minus h by 4 pi. We can see that here the spin angular momentum of the both of the spin states are equivalent in the magnitude, just differ in the sign. So one is having the plus sign and another one is having minus sign. Similarly, we can also define the magnetic momentum. So magnetic momentum of this plus half spin state is mu plus half is equal to gamma into S plus half, where gamma is the gyromagnetic ratio. Now when we substitute the S plus half, it will be plus gamma h by 4 pi. Similarly, mu minus half is equal to gamma into S minus half, which is equal to minus gamma h by 4 pi. Again, the magnetic moment is equivalent in the magnitude but opposite in the sign. By using these parameters, now we can define whatever the energy associated with the each spin state. So when we apply the external magnetic field, the nuclei can have the 2 spin states, and one with the low energy is called as plus half orientation and another with the higher energy is called as minus half orientation. And when we supply the electromagnetic radiation equivalent to the energy gap delta E, then the nuclei can jump from the ground state to the excited state. So in order to see the energy gap between these two spin states, let us define what is the energy of the plus half state and energy of the minus half state. E plus half is equal to mu plus half into B naught, because energy is equal to magnetic momentum into magnetic field strength. Now by substituting the mu plus half, this will be equal to plus gamma h B naught by 4 pi. Similarly, E minus half is equal to minus gamma h b naught by 4 pi. Now what is the difference between these two energy states? Delta E is equal to E minus half minus E plus half. So which is equal to minus gamma h b naught by 2 pi. When we subtract this, the denominator becomes 2 pi instead of the 4 pi. So here the energy gap between these two states is the minus gamma h b naught by 2 pi. Now if we supply the electromagnetic radiation having the energy equivalent to this energy gap, then the nuclei can be transferred from the ground state to excited state. So here the delta E is equal to h nu is equal to gamma h b naught by 2 pi. The sign is not important here, only the magnitude is important. So delta is equal to h nu is equal to gamma h b naught by 2 pi. If we cancel the h from this equation, then nu is equal to gamma b naught by 2 pi, where nu is the frequency of the electromagnetic radiation we have to supply in order to observe the NMR signal. Now what is the Larmor frequency? Just we have seen the nu is equal to gamma b naught by 2 pi, where nu is called as Larmor frequency. And nu is also called as precessional frequency because this is the frequency of the electromagnetic radiation which we have to supply in order to produce the resonance. And here gamma is the gyromagnetic ratio and B naught is the magnetic field strength applied externally. Now let us see how the signals are measured in the NMR spectroscopy. Let us take again simple example here, ethane. And ethane is having the proton which is having the I is equal to half, that can give the NMR signal. But this proton is surrounded by few of the electrons. Here the sigma electrons are present. These electrons are negatively charged and the nuclei is positively charged. So these surrounding electrons can show some shielding effect on the applied magnetic field. Suppose we have applied the magnetic field B naught in one direction, the surrounding electrons can produce their own magnetic field in the opposite direction. So now the magnetic field of the surrounding electrons is sigma into B naught. So the effective magnetic field B effective is equal to B naught into 1 minus sigma. So whatever the applied magnetic field is not completely conveyed to the protons because of the shielding of the electrons. But in the NMR we are not measuring how much is the shielding of individual protons, but we are comparing this shielding with a standard that is going to be taken in the NMR. So in the NMR spectroscopy, we are going to take a standard like the tetramethylsilane, which is arbitrarily given as a 0 value in the x-axis. And we are going to observe the peak of the sample at one position, suppose at the 2.1. Now the difference between these two peaks is called the chemical shift. So chemical shift is the shift of the peak from the standard reference peak. Tetramethylsilane is used as a standard which is having the high shielding. So it is arbitrarily given as a chemical shift as 0. If a proton is having the high shielding effect, it is going to fall nearer to the standard peak, so it will have the less chemical shift. So the proton is then going to fall in the upfield region. Similarly, if a proton is having the more de-shielding effect, it can fall in a area far away from the standard reference peak, and that region is called as downfield region. So in the NMR spectra, the shielding effect is inversely proportional to the chemical shift. Higher the shielding, lower the chemical shift. Now let us understand this concept by taking a simple example. Suppose we have a carbon-carbon hydrogen bond, and here this carbon cannot give the NMR signal and proton can give the NMR signal. Let us take another example where this carbon and hydrogen is attached with a chlorine. And we can also represent these structures as the Lewis dot structures. So here the first one can be represented as CH. So here the electrons are shared equally between the carbon and carbon because both are having the same electronegativity. But in the second example, we can observe the chlorine, which is an electron withdrawing group. So now because of the electronegativity, the electrons are going to be shifted towards the chlorine. This will generate the electronegativity on the carbon, so that the carbon will pull the electrons that are shared between the carbon and hydrogen. This is a negative inductive effect that is produced by electronegative atom chlorine. So if we see the Lewis dot structure, the electrons shared between the carbon and chlorine are going to be shifted towards the chlorine because of the electronegativity of the chlorine. And this generates a partial electronegativity on the carbon, which will pull the electrons towards the carbon. The electron density nearer to the hydrogen is reduced. So now this hydrogen is getting the de-shielding effect. In this way, due to the presence of chlorine, the electron density nearer to the proton is reduced, thereby a de-shielding effect is going to be produced. Now we can conclude that higher the electronegativity, higher the de-shielding effect. This de-shielding effect will reduce the electron density, thereby chemical shift is going to be increased. So we can further conclude that higher the electronegativity, higher the de-shielding effect, higher the chemical shift. Let us take one practical example here, and here let us see the number of peaks that can be observed. So here this is one type of proton CH3, and this is another type of proton CH2, and this is another type of proton CH2 which is attached to the Cl. You can observe that B and C are not equivalent. B is the CH2 attached to the CH2, but C is the CH2 attached to the Cl. So B and C are having the different environment, so they are not equivalent. So every non-equivalent nuclei will give one NMR signal. So here we can observe the 3 NMR signals, and if we see the position of these peaks in the NMR spectra, so this is the standard peak, and CH3 peak can be observed approximately around 0.9 ppm, and the peaks corresponding to the CH2 can be observed at this position, and peak corresponding to C can be observed at this position. And here, why the peak corresponding to C is having the more chemical shift? Because the protons indicated by C are attached with the Cl, where chlorine is an electronegative atom. Due to the electronegativity of the chlorine, the protons at the CH2 are getting the more de-shielding effect, resulting in the more chemical shift. So in a simple way, higher the electronegativity of the atom attached, higher the de-shielding and higher the chemical shift.